Okay, thank you, and thank you for the invitation to this workshop. I'm Søren. I'm from VIA University College in Denmark. I'm head of the research program for energy and climate. And I'm here to talk about technical and commercial development of fifth generation district heating and cooling. And just as Søren, I'm going to use ThermoNet for the rest of the presentation because it just rolls off the tongue a bit more easily. I will try to flesh out some of the points that Søren has made in terms, especially from the technical point of view. What is the added value we get from these systems? Søren has already talked about this shift in paradigm, and it is very difficult. It's something you have to be humble about. There's this nice figure that sort of tells you if you have to go from research and invention and to commercial application, there is a very difficult phase that you have to traverse. And the reason for this is as your TRL or your technology readiness level declines, the funding declines as well. And at this particular point, there may not be a lot of private financing or investment that wants to pick up the technology. So you have this minimum of funds being allocated into this new technology. And you end up in this, what some refer to as the valley of death. A lot of good technologies have died here because no one really understands how to get through this phase. And this is something that you will have to do as well here. You have to get across the bridge and not fall off and end into the valley of death. I'm a researcher myself, but I think I've realized in my career that as a researcher, I don't really have any impact. If I want to have an impact developing new technologies, I have to get across this bridge and into commercial application. This is where you have an impact and you can make a change. So this is what you have to focus on. So what do we find in the valley of death? There are many things that can go wrong. There are competitors. And then there's what we call the value proposition. What is it that we can provide with this new technology that is better than our competitors? If we can't say it in really plain terms, really quickly, then the competitors are going to beat us at it. So this is really key to commercial application. Once you have a good value proposition, you also need to address issues like business models and risk management. So who's going to own what? Who's going to be the operator? Who's going to take responsibility when things go wrong? And so on. This is also extremely important, obviously. Then typically on the national level, you have different types of legislation and regulation that applies. There may be some EU regulation, but usually on the national levels, some legislation applies that you need to deal with, you need to understand it fully, and you need to address it completely and consistently. Then we have the entire value and supply chains. They have to be able to work with this new technology, not just work with it, but also work with it in an efficient way so that you are cost effective. So there's an entire sort of phase, some refer to it as the instrumentation of the value chain. That is the education of the value chain for working with this new technology. And obviously, maybe you need new products and different components of your solution that the supply chain has to be able to produce, also at reasonable costs. Then there's the status quo, and Søren has already mentioned this. This is a really tough competitor for new technologies because people like to stick to what they know and what they do. Business as usual, as it says here. And also, you usually also have to fight commercial interests. So one thing we're fighting at the moment is hydrogen for home heating. It's the most insane, stupid idea that has ever come about, but still people are trying to push this as a green solution. So as you're traversing this valley of death, you constantly have to battle these insane ideas that should just die off. Finally, perhaps the most important is financing and potential government incentives that you can funnel into the cost structure of the technology. So usually green technologies have large upfront costs, and you need some way to deal with this so that it doesn't hurt your value proposition to the consumer. usually consumers are very focused on the upfront cost. So you can't explain to them, well, in 20 years this will be cheaper. Yeah, but right now it's going to cost me a lot of money, so I'm not going to say yes to it. So you need consistent financing options, and you need to explore possibilities for government incentives. And there are probably many more, and I'm sure that Lisa will also get into this. Okay, so I'm a researcher, so my focus will be on sort of the new, crazy, wild ideas with ThermoNet, because one thing you can use to characterize this new generation of district heating is that it's extremely flexible in terms of heat sources, and that's because we have ambient temperatures. So we can use pretty much any resource as long as it's sort of lukewarm. So in Denmark, when we talk about value proposition, we use the 4 Ks. That doesn't work in English, but in English you can replace it with 4 Cs instead. It's climate, it's cost effective. If you do it right, it's cost effective. It's comfort. You have both heating and cooling. And if you do it right, it's also comfort in the solution. Someone takes care of it. I don't have to think about it. I don't have to own anything. So that's another type of comfort. It's also a clever solution. And often the clever solutions are difficult to deploy because people don't understand them. So I want to focus on one particular aspect that I've been looking into more consistently recently, which is sector integration. So as you can see on this figure, there's a lot of different sectors that can contribute energy to our thermonets. We have industrial heat, process heat. We have electricity, for instance. Surplus electricity can be converted to heat. Rainwater, drinking water, wastewater. We also have foundation piles. Maybe some of you are familiar with this technology. Energy piles. So an energy pile has 2 purposes. It serves as a way to ensure structural stability of a building. So it's something you have to put in the ground no matter what. It's a sunk cost in that sense. It's infrastructure that we have to build no matter what. The cost of adding a few pipes to these piles is very low. We did a research project where we found payback periods for energy piles, also for district heating, 4 to 6 years, because the upfront cost is really severely reduced. So the whole idea about sector integration is very interesting from a cost efficiency point of view. We can integrate with the water sector pretty easily also. In Denmark, we have a lot of rainwater. We have constant problems with surface water and flooding. And there's a lot of energy in this water, and it's easy to utilize. Also wastewater, this is always present and easy also to utilize. So there are many possibilities, and this is going to be the theme, at least of the first part of my talk. So we have proposed a new type of energy geostructure. So energy piles are a part of what you call energy geostructures. It can be tunnel walls, diaphragm walls, all these kind of structures in the ground that we built. We can use them to exchange heat. So we've been working for about 4 years now on a new type of energy geostructure where we use roads, which is an essential part of our infrastructure, as a new type of energy geostructure. The idea is to combine a sustainable urban drainage system with a geothermal heating and cooling system, that is a thermonet. And then we combine 2 sectors. That is, we combine water management with energy supply. So we get a sector-integrated type of supply that has more than one functionality. So the basic idea is to use the geotechnical structure that we have below pavements to ensure that when a truck drives over the pavement, it doesn't crack, it doesn't move. We refer to this as the roadbed. It's typically made up by gravel that is porous, so it can contain water. So when we have problems with flooding in Denmark, this could serve as a potential basin for storing water. the second idea is to put geothermal collectors into the roadbed as well. So we are digging this hole no matter what. We might as well put in several things that serve several purposes. That is to use existing infrastructure that has to be constructed no matter what. So this is sort of the idea. You can see the black geothermal pipes of the thermonet. We have the drainage pipes in the sides that drain off water to a water break. So we have a controlled discharge. No matter how much water is in the roadbed, we have a controlled discharge to the sewer system. So we create synergies from combining these two types of utility and supply. So there's a benefit for our thermonet, and that is that we increases the heat extraction because we are trickling water on these geothermal pipes, so we see improved heat extraction. Another issue is also water quality. So that means that road water is pretty dirty, full of all kinds of things. So you need some sort of process to clean up this water, both biological but also chemical processes. And this structure serves basically as a large filter where all kinds of processes can occur. So what we've seen is, we've done a PhD project on this, is that the water quality is very much improved once it exits the roadbed. So this is another added value from this sector integration. So now you can see the functionality stacking up by using the same infrastructure. So this is a way of dealing with these large upfront costs. Yeah. Okay, so we actually built this in full scale. So it's always nice to have these drawings where you can have a lot of good ideas, but when you have to build it, it's something completely different. So we have 50 meters of road somewhere in Denmark. It can contain 120 liters of water. This corresponds to 300 millimeters of precipitation if the roadbed is empty of water. That's a lot of precipitation. It supplies a kindergarten with space heating and domestic hot water. Here you see some pictures. The roadbed with the geothermal piping, bentonite lining to hydraulically separate the roadbed from the surroundings so that we don't have uncontrolled seepage into the roadbed. This is very important. We use permeable asphalt shown up to the right. And you can see the traditional asphalt next to it, 25 meters each with these two types of pavement. So we put the system into operation, supplied the kindergarten with heating and domestic hot water, and we monitored the brine temperature. That is the temperature in the grid temperatures for this period here, a couple of years. And then we tried to model it with a computer model, a mathematical model that we developed. The details are pretty gory, so I'm not going to show those, but you can read the paper on this. So with this model, we can explore different sort of scenarios. And I want to show you some of this added value. One could ask the question, what is the impact of infiltration on our heat extraction? Well, obviously it's positive. If you look at the blue curve, then you have increasing infiltration to your right of your x-axis. And you can see an increase in heat extraction that goes all the way up to about 35% if we infiltrate a lot of water, 2,500 millimeters per year. So the next question is, what if we want to do seasonal energy storage? That's another hallmark of thermonet. That is that we can inject heat into the ground and then use it later on. Is this eroded by infiltrating water? It turns out the velocities, the groundwater flow velocities, are low enough to preserve some of this energy. So the red curve shows this shift upwards in heat extraction that you gain from fully balancing the ground. That is, you put as much energy into the ground as you extract during winter. So this is added value. This curve that goes up, this is added value for combining, or synergy from combining these two types of utility. So we found in this paper that the climate road can supply 3 to 4 new family dwellings, and that's pretty much what you can fit along 50 meters of road. The infiltration increases the heat extraction by 26%, and seasonal heat storage can increase this number to 56%. So the idea is that when we have these dwellings, we take the water from the roofs and so on, and we direct it into the roadbed to prevent flooding. So this is a key feature. So we took this idea even further to see can we do even more, and this is the second version that we have worked with, and we have actually done a full-scale demonstration of this as well. So we have, in this second version, established a thermonet as well. We have individual heat pumps in the buildings. Now we have borehole heat exchangers. This is mostly for backup reasons, but also to be able to supply consistent cooling, because the roadbed tends to get warm in the summer because of the close proximity to the ground surface, but also the very hot asphalt, which actually contributes quite a lot of energy. Then we have a heat exchanger along the central wastewater pipe to reclaim some of that energy lost from the domestic wastewater. And there you see the water break to have this controlled discharge to the sewer. So this is combined energy efficient, sustainable district heating and cooling and surface water drainage. We call this the thermal road. So here you see it, the big manhole, concrete manhole in the front of the picture is where we have the water break. This is very essential. To create value for the wastewater company, you have to be able to guarantee that the discharge rate is at a certain level all the time. This is the idea of retardation of water. Benzonet lining and the geothermal piping again. And in the back we have the borehole heat exchangers. And then we have this very large manhole. This would not look like this in a commercial application. It's 2.5 meters in diameter. But it's because we have a lot of measurement devices. We have temperature sensors, flow meters, and so on every source. The next step now is to actually sell those parcels and populate them with houses. And we're struggling a bit with that. But once we put it into operation, we'll have a system that is extremely well monitored. And so we can use a case like this to validate models and so on, and also as a showcase. Actually, the latest development is that one of the biggest contractors in Denmark said, we would like to do a case here with really lovely buildings and so on, but the municipality has said no, as they often do, because if the computer says no, then we can't do it. So again, you have this resistance in this valley of death. This is the road pavement, and you can see the connection pipes to the left, the blue pipes, or no, the black pipes protruding from the ground. So you just connect your heat pump and then you're going. Okay. Now on from this sector integration, I want to finish my presentation with some ideas and concepts from this project, Cool GeoHeat. This is an Interreg project with these partners shown here, where we try to do a more sort of holistic view on everything that is related to deploying thermonet. So these are the different work packages that tries to go around all these aspects, both technical and commercial, operational data for one. Do we have any operational data from existing systems in Denmark? And what we find is, because it's commercial application, there's pretty much zero, because there are no money for instrumentation or measuring devices. These operational data can be used, as I mentioned, to validate design models, to see that they actually are in line with the real world. And design models are necessary for our business models, because if we have to predict some sort of cost of a new project, we need design models, because it's important to know how many borehole meters do we need, because they are quite costly and so on. All this stuff feeds into a best practice that we finished the project with. This is a finished project, and we did so with a stakeholder group to get some input from the outside world. So we did a case study on a thermonet in Denmark, this thermonet in Silkeborg at Balle Bygade. It's a very small thermonet, not too small. We have 15 houses, 14 new builds, 1 existing house. So you have different heat pumps, 6 kilowatt for the new houses, 10 kilowatt for the existing house. We use 6 geothermal drillings as a heat source, drilled to a depth of 120 meters. The interesting thing about this case is that this grid is actually owned and operated by Silkeborg Utility. This was a research project, but the business model turned out to be that it's the publicly owned Silkeborg Utility who owns the grid and also the heat pumps. So this is an interesting business model. Here you see the layout. This is how such a grid would look like. This is as built, so these are measurements of the actual positions of the pipes. You have the 6 borehole heat exchangers on a line to the left, placed very conveniently in a noise barrier, so it's protected from surface water getting into the boreholes. That's a threat to water quality in the subsurface. So that's another added benefit from not having boreholes at each individual parcel, that you have control over where you place your drilling so you can better protect the subsurface. We have 1,340 meters of horizontal pipes, and don't forget, in traditional district heating, this is not an asset. It's a source of loss. You lose about 20% of your heat in traditional district heating. Here, it's a part of your production capacity, so it's an asset. It adds production capacity, and I'll show you how much. So we built a digital twin of Silkeborg, so we need these models, as I mentioned, to be able to make predictions about these systems, both from a technical point of view, but also from a cost point of view. So we use the Modelica platform. Some of you are probably familiar with it. It's a very powerful way of modeling complex connected systems. So we have models for boreholes, we have models for heat pumps, and then it's possible for us to connect it into a very intricate model of these systems. On top of it, we've added a cost module, so we get the life cycle costs when we do the technical simulation. So very nice tool. But also very sort of elaborate. So you get a lot of interesting key performance indicators from these simulations. You get the brine temperatures, for instance. That's vital to your performance. You can't have brine temperatures that are too low, or in case of Spain, too high if you do a lot of cooling. You get the thermal exchange in the grid itself. You get the seasonal performance factor, which we know for Silkeborg is, for odd reasons, it's not very good. But we also get that with the model. So obviously, maybe we can solve this problem by using the model. But notice here, CPU time, 3.5 years simulated, almost or 3/4 of an hour. This is not practical for a company to use Modelica. So this is a research model. So we've been working on a fast design model at VIA. I started the development of this code last summer because I thought this is necessary. This design model is much faster. As you can see, it takes less than 1/10 of a second to run. It gives you, provided all the necessary information, it gives you what kind of pipes should I use, how big should they be, what is the production capacity of the grid itself. In this case, for Silkeborg, it's around 30%. So we get a 30% of the peak load production from the grid itself. So the take-home message here is you need to look at the graph to the right. If we had to do individual solutions for these buildings, we would need 1,345 borehole meters. That's quite a lot. The Thermonet is built 720 meters, a great reduction. Where does this reduction come from? Thermal capacity in the distribution grid, and then diversity factors also apply. Diversity factors means that when you have peak demands in one house, it's extremely unlikely that you have a peak demand at the neighbor at the exact same time. So peak demands don't stack up when you connect people in a grid. In fact, the diversity factor here is about 2/3, so 65, 66%. So that reduces the need for borehole meters. Now, if you balance the ground, you can reduce the amount of borehole meters you need by even further. That is, you add the energy to the ground that you subtract. So we can go down to 570 meters according to this tool here. So clever use of resources, more efficient use of every borehole meter. This is what you also get with Thermonet. We developed some business models that can probably work for Denmark. The first model is split ownership, not so different from Ken's model. We have a private entity of some sort. We don't really know what that is, but it could be this company, Sustain. They will use pension funds to mature a project, plan it, and also get the decision phase done, and then constructing the grid. Once it's up and running and the risks are gone, they hand over the keys to the district, to a public district heating company. So the ownership changes. The district heating company owns and operates the grid, but the consumer owns and pays off the heat pump. And these heat pumps are procured in large quantities by Sustain to get those benefits from buying large volumes of heat pumps. You would never be able to get that as a private consumer if they had to buy, each had to buy the heat pump. The second model is that it's the public district heating company that will do everything, and they'll also own the heat pumps. In this case, the model that is used in what Søren showed in Vridsløse Magle. Okay, so just a few concluding remarks. Be aware of the valley of death. So I really want to stress that ThermoNet is a well-proven technology. So don't get lost in more research projects. Don't get lost in many demonstration projects. Try to find a template that works, that you can replicate again and again. So focus on commercial development. Define a value proposition that is desirable to the decision maker or the end user. Otherwise, they're going to turn it down. I don't know who that would be in Spain. Then determine what is required for this value proposition in terms of the upfront investment and variable costs. Is it competitive? What type of cost structure is the end user willing to accept? Business model and risk management. Who owns what and who's the grid operator? The organization, this is also very important. Who supplies the solution? You can't have a lot of different actors. You need some sort of unified approach. Consider a one-stop shop concept. That seems to be a common theme to those that are actually successful at commercial application. Financing and government incentives. Aim for consistent financing solutions and fully utilize incentives if such are available. So this is the work you need to do. All right, thanks. That's all I have.